We're going to start the session. The first speaker in the morning is Daniel Eisenstein from the University of Harvard, who will be talking about measuring the cosmic distance scales with SLOAN 3.
Well, it's a great pleasure to be here today to talk to you about SDSS-III at this momentous time in cosmology. I think I may be the first speaker from outside the Planck team, so I want to congratulate the Planck team on this very major achievement. I'm going to focus here on our results from SDSS-III and mostly on the baryon acoustic oscillations. And of course, the reason for the emphasis on the cosmic distance scale is dark energy, which has reinvigorated our interest in the cosmic distance scale and in the behavior of gravity and seeing how we can measure this to very high precision. So the outline of the talk, I'm going to introduce baryon acoustic oscillations as a cosmic standard ruler. I'm going to try to describe the linear theory very briefly, talk to you a little bit about some nonlinear aspects of the BAO, and then I'm going to turn to data, and in particular results that have come out in the last 15 months, both from SDSS-II and SDSS-III, and highlight this as a mechanism towards moving towards the future, the rest of the decade, and the BAO results that are coming out. Okay, so we saw nice pictures yesterday of the acoustic oscillations, but we didn't actually hear very much about the physics that caused them. I want to particularly acknowledge that Jim Peebles and Rashid Sanjayev are here, two of the people who really led the development of this work back in the 60s and 70s. So the idea here is that if you have some initially overdense region of a universe with adiabatic perturbations, then that region is also overpressured. It launches a spherical sound wave out into the ambient medium. This wave travels out at relativistic speeds until you get to the epoch of recombination. At that point, the universe becomes transparent, and the photons that are providing the pressure to the gas stream away, and the gas stalls at a co-moving radius of that is today 150 megaparsecs. So you end up in this situation where you have dark matter in the center, gas in this spherical shell at 150 megaparsecs, and both of these regions seed the formation of galaxies. And so our observable at the end is that we should see pairs of galaxies separated by this distance of 150 megaparsecs. So the reason that we care about this so much is that this distance of 150 megaparsecs can be computed from very simple physics. It's just the distance that the sound waves could travel from the Big Bang until the epoch of recombination, and that turns out to depend upon very simple quantities. It depends upon the inertia in the fluid, which we usually write as the omega baryon h squared, the baryon to photon ratio, and it depends on the amount of time the wave had to propagate, which depends upon the amount of time the universe spends in the radiation-dominated phase compared to the matter-dominated phase, which depends upon omega matter h squared. If you have these two quantities, then you can compute the sound horizon, this distance of 150 megaparsecs exactly. And the wonderful thing is that the microwave background anisotropies, the relative heights of the peaks and troughs in the power spectrum, allow us to compute exactly these two quantities. And with modern data, this allows us to calibrate this length scale to below 1%. In a redshift survey, we then get to measure this in two different ways. We get to measure along the line of sight, which exposes the Hubble constant at that redshift, the Hubble parameter at that redshift, or we can measure it across the line of sight, which measures the angular diameter distance as a function of redshift. So if you have surveys at a variety of redshifts, then in principle you can map out dA and h of z over those ranges of redshifts. So of course the way we like to do this is with redshift surveys, is the way that we can actually measure the three-dimensional clustering of matter. But unlike the CMB, the perturbations are no longer tiny, and we have to worry about complications from nonlinear structure formation, from galaxy clustering bias, from redshift distortions. And these things all degrade the acoustic peaks at a mild level, but because the scale of 150 megaparsecs is a very large scale compared to the scale of galaxy and cluster formation, the signal is preserved even to low redshift with good contrast. So let me turn now to the topic of nonlinear structure formation. So the idea here is that this acoustic signature is carried by pairs of points that are separated by 150 megaparsecs. But at low redshift, the nonlinear formation of superclusters has buffeted both points around by of order 10 megaparsecs. And so what began at 150 megaparsec separation has been moved to 140 or 160 megaparsecs. So this broadens out the acoustic peak, here shown in the correlation function, and that broader peak is therefore harder to measure and harder to centroid, so it's hard to get the scale. However, to actually move the scale requires that you have net infall or net outflow at 150 megaparsec scale. So you have to systematically move 150 towards 149 or towards 151. This is actually a much weaker effect. Depends only on the overdensity inside the sphere, which is typically of order 1%. And in fact, the overdensities and underdensities partially cancel, so the mean shift is quite a bit less. In simulations, we've now shown that this acoustic peak, oops, sorry. Where am I going here? This acoustic peak shifts are about 0.3% by redshift 0. It's a very highly predictable signal. As you go to galaxy bias, then you shift the relative weights of the inflows and outflows, and this can produce an additional shift of order 0.5% in extreme cases. These effects are very well matched by second-order perturbation theory, so we actually do have an analytic understanding of the shifts in addition to the direct simulation. And it turns out that we'll actually be able to remove these shifts entirely and get to essentially an unbiased estimate. So the way that we do this removal is with this idea of reconstruction. I said that the reason that the acoustic scale has been moved around is due to these large-scale flows, but these flows are produced by the same gravitational sources that we're actually measuring in our map. So when we make our galaxy redshift survey, we're actually mapping out the large-scale density field. We can predict the large-scale velocity field, and when you then remove that, then you actually restore the field back towards the linear regime, the input field, and you can restore your statistical precision, and it turns out that you can also unbias the field. So this is just a cartoon of this where I've marked the points at the center of the ring with blue and some points here with black, and this is a Gaussian sort of showing the width of the black points relative to the red curve, which is a ring at constant distance from the blue points. And if I now, where am I? Okay. If I now let this movie play, then we'll start forming structure, and you can see that the black points start to deviate from the red ring. And the width of that is broadening out this acoustic feature. That's the sign of the large-scale flows. Oh, come on. So you can then estimate the velocity field from the density field. And on large scales, you can start to move things back. It's hard to fix the small scale structure well, but if you can just tug the large scale features back towards the initial field, then you can sharpen up the acoustic peak a fair bit. So that's the idea of that. So when we do this in simulations, it works very nicely, and it not only reduces the error bars, but it removes the shift down to a level of 0.02% in the matter case, about 0.1% in the galaxy case. That's actually limited by our simulation volume. And even when we do this on full cut sky, in-body mock catalogs, we find that we've removed things down to a small fraction of a percent. And the reason is pretty clear. It doesn't really matter how you're tracing the large-scale flows. If you can remove the large-scale flows, then it doesn't matter how the bias has actually traced them. Okay, so turning to the observational side, just briefly, I want to point out that in general, the BAO application is considerably easier than general power spectrum analyses because the BAO signature is so oscillatory. So you get this extra factor of differential structure in your results. So normally in most observations, one's very concerned about broadband tilts, broadband errors that might affect large scales compared to small scales. And these things tend to be very smooth. But it turns out that in the case of the BAO, we're not actually very sensitive to these. We explicitly marginalize against these broadband tilts. And what we're really concerned about is how to measure the left-right position of these peaks rather than the up-down position of this curve. And it's worth noting that this length scale is tied directly to measurements of angles on the sky and redshifts, which are two things that astronomers measure extremely well. basically parts in 10,000 are really easy. You can do parts in a million if you need to. So it's much better than the type of precision of 1% or 0.1% that we're interested in the data. So turning now to the observational results. So just as a brief introduction to the SDSS, of course, this is the world's largest galaxy redshift survey. And I just want to highlight here that I'm going to be talking about two different data sets. The first is data release 7, which is the full data set from SDSS 1 and 2, and is the original coverage of the sky with galaxies out to redshift of 0.5. And then I'm going to turn to data release 9, which, although it sounds like only slightly larger than data release 7, is actually the first spectroscopic release from SDSS-III, which is a new survey covering the same region of sky, but now out to higher redshift and with denser sampling, going out to redshift of 0.7. So just to bring you up to speed towards the past year, in 2009, Percival et al. And Reed et al. Produced the power spectrum from the full SDSS-II DR7 sample along with the 2DF Galaxy Redshift survey. And this produced a BAO signal that was a 2.7% measurement of the distance to redshift 0.27. And this gave very nice agreement with the lambda CDM model with H0 around 68, omega matter about 0.29. In 2011, there were new results from two surveys on the Anglo-Australian site. So the Wigglesy survey on the 4 meter and the 6DF Galaxy survey on the Schmidt. And these both gave BAO detections, one at very low redshift and one at higher redshift. So this was a very exciting development because we are now getting to have a real Hubble diagram with the BAO method. So turning now to the last year and a half, in early 2012, Padmanabhan, Xu, and Mehta presented a new analysis of the DR7 data, including reconstruction. So I'm just going to go through this to try to show how that played out, and then we'll turn to SDSS-III. So this is a plot of the correlation function in real space. This is r squared times the correlation function. This is distance along the line of sight, distance across the line of sight. And so you can see the BAO ring here. These are from mock catalogs, a big stack of mock catalogs. This is far more data than the actual DR7. So this is in real space. When you turn on redshift space, you see a very strongly anisotropic signal. And to demonstrate that reconstruction is doing something useful, this is the result after you apply reconstruction to these mock catalogs. So we have been able to remove a lot of the velocity effect and actually sharpen up this acoustic scale on large scales. So you can't fix the anisotropies on small scales in full, but it really does very useful things on large scales. So in the data, this took things from a correlation function like this with a 3.5% error to this correlation function with a 1.9% error. So this gave us a 1.9% distance to redshift of 0.35, and just this one step of reconstruction was equivalent to tripling the volume of the survey, which takes you from a 7-year survey to a 21-year survey, so that was a useful thing. Okay, so now turning to SDSS-III. SDSS-III began in summer 2008 and will be running until 2014. It's actually composed of 4 surveys. I'm only going to be talking about the first one, the Baryon Oscillation Spectroscopic Survey here. This is a large survey for large-scale structure. And SDSS-III is supported by the Sloan Foundation, the US Department of Energy, and National Science Foundation, and over 50 member institutions from around the world. Some of the members are here in this room. It's a large list of institutions that have come forward with support for the project, and it's been a very successful collaboration. Okay, so BOSS is intended to be a comprehensive study of the low redshift acoustic oscillations. In terms of number density versus redshift, it looks like this, but if you scale to a volume, you can see how, so the red and the blue are the new data compared to the old data. You can see how much of an extension this is. So this is 10,000 square degrees of spectroscopy out to redshift about 0.75, 1.5 million massive galaxy spectra, and also a set of quasars at redshifts greater than 2 to look for the BAO and the Lyman alpha forest. I'll show you those results in a little bit. So the data that I'm going to be talking to you about is the data from data release 9, which covered this geometry on the sky. This was about 1/3 of the final survey, but we now actually have over 80% of the data in hand, so the survey's very nearly complete. So in this DR9 data, we saw a very clear detection of the acoustic peak. This was published last year. We did analyses in both the correlation function and the power spectrum and got a 1.7% distance to redshift 0.57. The agreement with 0.35, with the SDSS-II data that I showed you earlier is really very good. We see the peak in exactly the same location. And the difference here in amplitude is just because the boss galaxies are a little bit less massive and a little bit less biased than the SDSS-II galaxies. So very nice concordance between the two data sets. The boss detection itself was a 5 sigma detection, which is the first time the BAO has been detected in a redshift survey at that strength. But combined with SDSS-II, the detection was over 6.5 sigma. So it's really going to be a very nice detection of the BAO. So we saw some of these plots yesterday, but here's the latest Hubble diagram from BAO. And the line here is from the WMAP7 data, but this is a prediction. This is not a fit. This is assuming that the WMAP lambda CDM fit, and you can see how nicely it goes through the points. If you divide by that WMAP fit and look at the residuals, you get this. And the gray zone now is the uncertainties from WMAP. And if you just move the WMAP omega matter h squared up by about 1 sigma, then you get to our best fit through the data. So it's a very nice match. The Planck data is gives you error bars that are about half as big, and it shifts up to a little bit higher than the dashed line. So this is a very nice match. George showed this plot yesterday from this paper 16, which is the same plot but flipped upside down, and but beautiful match to the BAO data. The BAO Hubble diagram is also very consistent with supernovae. If you take the SNLS data and normalize it to BOSS, then you get this swath of predictions to lower and higher redshift. So you can see how well that goes through the general BAO, and in general how well it matches to the lambda CDM cosmology. So as the gray swath that I've been showing up to now is assuming lambda CDM. If you vary either the equation of state or you vary the flatness assumption, then these curves move. And in particular, if you make the universe 1%, I guess that's open, then you get to the blue swath. If you make W of minus 0.7, then you get to the red swath. So that you can see how much cosmological leverage this data has. And of course, the data as it stands is very consistent with the flat lambda CDM cosmology, as I think the Planck papers very nicely show. One thing that's important to think about is that when you consider the measurement of H0 and omega matter, if you combine the cosmic microwave background, the BAO, and the supernova, then you produce what I call a reverse distance ladder, where the CMB data with omega matter h squared and omega baryon h squared is measuring this sound horizon at redshift of 1,000, so it's calibrating a distance at redshift of 1,000. The BAO is then measuring this at redshifts of order 1/2, and then the supernovae empirically are taking the redshift 1/2 distance down to redshift of order 0. So you really are measuring, you're making a prediction for H0 at low redshift, independent of what you think the dark energy is doing or what the curvature is doing. And so, in particular, you get very strong constraints on H0 and omega matter, independent of what cosmology you pick for your model. So this is open W all the way up to open W0 WA, and frankly, I could keep going. You really get very consistent constraints on this. With WMAP7, this was H0 of 70 and omega matter of 0.28. With the Planck data, I'm sure this would be a slightly lower H0 and a slightly higher omega matter. Okay, turning now to the question of anisotropic clustering. So, as I showed this figure before, clustering should be isotropic in real space, but if you use the wrong cosmology when you measure your correlation function, then you generically produce an anisotropy, which is often called the Alcock-Paczynski effect. This will create a distortion in the ring. So this circular ring would become elliptical with a factor of that depends upon the angular diameter distance times the Hubble parameter. But beyond the BAO, there's far more information on the Alcock-Paczynski effect at smaller scales. Clustering should be isotropic all the way down. And if you can model the smaller scales well, then you can extract more information. The problem is that redshift distortions are also producing a very strong anisotropy, and that gives you an order unity anisotropy. And so to measure the Alcock-Paczynski effect to 1% or below, you need to be able to model this anisotropy quite well. But of course, there's a lot of interest in the redshift distortions for their own sake, because this large-scale velocity field is a test of the growth of structure, and that's one of the key tests for modification of gravity and as a possible explanation for dark energy. So we definitely have an interest in separating the two. They do have different scale dependencies, so in principle one can separate the two. And this is just a process that will be continuing in development from today with data sets like SDSS-III and Vipers all the way to Euclid and beyond. So it's just a major point of interest. So we've produced a set of papers in the last month on measuring the BAO anisotropically in DR9. So here, for example, is the correlation function in the direction transverse, on the sky, and here's the line of sight. So you can start to see this acoustic ring in both directions. And I think one of the major outcomes of that for me was that it shows that this typical combination that we measure when we spherically average the correlation function, this quantity dV, is actually a good compression of current data. So the green points here are what you get if you measure the full constraint on distance along the line of sight and distance across the line of sight from the full monopole quadrupole data. And the blue is what you get for a swath of constant dV. So I think this was just showing that dV was a good compression. That was not completely obvious going in. There have been several analyses in BOSS studying the Alcock-Paczynski effect and the growth of structure. Here's an example from Reed et al., where they measure the quantity F sigma 8, which is related to the redshift distortions, and the quantity dA times H, which is the Alcock-Paczynski effect. The green swath is the CMB prediction, the blue swath is the measurement from the data, and the red swath is the measurement if you force the Alcock-Paczynski effect to the measured distance redshift relation. So this is just trying to get a feeling for how well we can measure redshift distortions. And it works out to be of order, the precision on sigma 8 works out to be of order of 5%. It's very consistent with the measurements that have been made elsewhere. Unfortunately, we're not quite at the level of precision to be able to split this difference between the Planck values around the low 0.8s to the cluster values in the mid 0.7s, but hopefully we'll get there soon. So as the final piece of observational data, I want to show the results from the Lyman alpha forest. So this is work that's come out late 2012 from Buska et al. Reporting reporting a first detection of the acoustic peak in the Lyman alpha forest. So this is using a set of 48,000 quasars at high redshift, where we're cross-correlating the Lyman alpha forest in one line of sight to the Lyman alpha forest in another line of sight. So most Lyman alpha forest work to date has been using the autocorrelation along a single line of sight. Here we're using this denser grid of quasars and doing the cross-correlation between many points. And this gets a tentative detection of the acoustic peak, but already this is allowing us to measure the Hubble parameter at redshift 2.3 to below 4%. So this is really stepping out to a very different redshift range with these precise distance measurements. In February, I think Azra Slozar and David Kirkby led papers getting similar results on the same data set with a different analysis. And here's their measurement of the acoustic peak. So one of the nice aspects of this is that if you measure the Hubble parameter as a function of time, you can actually, the previous data was showing this acceleration at low redshifts, but here's a point out here that really is showing that the universe did decelerate from redshift 2 to redshift of order half. Not a great surprise, but it's just nice to see it actually coming out in the data. Okay, so that's where the BAO stands today. There's just an enormous amount of effort going into this field at this point. So SDSS-III BOSS is underway. We've had our first results, but they'll be of order 3 times more sky area and actually a broader redshift range by the end of the survey. There's a new project called HETDEX, which is going to be starting, I think, in 2014. This is measuring Lyman alpha emitting galaxies at redshifts above 2. And there's lots of surveys planned for the remainder and end of this decade. There's EBOSS, MS-DESI, Foremost, Weave, Samire. I hope I haven't missed one, but I might have. So there's lots of projects going on at redshifts 1 to 2. The Euclid mission is then going to be a major stand for this, with of order 50 million galaxies at redshifts 1 to 2. WFIRST is planning to do a deeper survey over a smaller area. And then the other thrust in this field is the 21 centimeter ideas to look for BAO in redshift 1 to 3 with either with dedicated near-term instruments or with the SKA, the Square Kilometer Array. So there's just a huge amount that's still out there to be done with large-scale structure. We're very excited about it. If you're interested in learning more about the BAO or about other techniques used to measure dark energy, for the students in the audience, I wanted to point out this review that David Weinberg led us in. That's a very lengthy review of various observational methods, supernova clusters, weak lensing, BAO, and others for the study of dark energy. So this might be of interest to you. And I'll just conclude that the acoustic oscillations are providing a robust way to measure the Hubble parameter and the angular diameter distance. It's a very clean signature in galaxies. It's well protected from the types of systematics that we often worry about. And you can probe over a range of redshifts, including out to a connection directly to redshift of 1,000. You can probe the Hubble parameter directly, which is a particular value at higher redshift. To date, we've used the acoustic signature to measure the distance to redshift 0.35 to 1.9%, to redshift 0.57 to 1.7%, as well as a first detection at redshift 2.3. And all of these are providing very excellent consistency with the flat lambda CDM cosmology. But this is really just a taste of what's going to be coming in the next decade with large surveys that are going to be pushing us to 1% and probably down to around 0.2% by 10 years from now. So thanks very much.
Thank you. We have some time for questions.
Thanks for this very nice talk. Seems to me that from what you showed and what we see, these data are dominated by noise, basically, by statistical errors.
That's right.
Still, I would like to ask you, you convinced us that a lot has been done to control the evolution aspect of the systematic potential effect. What is, at the moment, in your view, the most worrying, if you can say, systematic potential systematic that could affect the data? Where are the things that could limit, let's say, the statistical compression?
Right. So with one caveat, which I'll get to as the second part of my answer, I actually think that this method will be statistics limited to the cosmic variance limit, assuming that we pay attention to what we're doing. I don't think there's any show-stopping issues. Today, our systematic errors are well below our statistical errors. So the one caveat there, the only astrophysical effect that I know of that could cause a systematics is this relative motion of baryons and dark matter that was discovered by Silyakovich and Harada, where at redshifts of order 20, there's a small mean streaming velocity between the baryons and the dark matter, which is enough to affect the collapse of the earliest mini halos. And so if one thinks that probably modulates the formation of early stars, first stars, at an interesting level, and if one thinks that formation of first stars then has an effect all the way up to galaxies of order 10 to the 11 solar masses, then in principle one could, because that effect knows about the acoustic scale, then in principle you can move the acoustic peak. Now it's been shown that this produces, if it moves the acoustic peak, then it will produce a very measurable, distinctive signature in the 3-point function. So I actually think that this effect will be controllable as well. But it's fair to say that today we have not measured that 3-point term. So in principle, that would be the one astrophysical systematic. I think the people who generally work on the early galaxy, on proto-galaxy formation, don't tend to think that there will be a signature as you move up to scales that are 100,000 times more massive than the mini hails that are affected. But I think it's conceivable that it's important that we look for this 3-point configuration.
More questions?
So Daniel, I have a related question, which is how reliable is the 1.9% error? I mean, there are certain things that are not propagated through self-consistently in your error model. For example, the way that you fit the redshift distribution and so on.
I don't think that one comes in very much, but we do treat the mock catalogs the same way that we treat the data. So it's not that we're assuming. So we do fit the N of Z in every mock catalog, and that does come through in the error. I don't think you can move the error bar very much. It's always the case that one can always argue about the error at 5 or 10%, like in almost any data set. But I actually don't think that it's very bad. I think that the big change for us has been moving from 3 sigma detections to 5 sigma detections, because that just improves the Gaussianity of the tails of the likelihood function so much more. So I think that's an aspect that we're very glad to be past.
So what kind of error bar do you project to get for the Lyman alpha forest, and how do the systematics for the forest differ from what HETEX will see by looking at the galaxies at the same redshift?
Okay, I'm not actually remembering the exact forecast for the full forest. It'll be of order 2%, but I'm not remembering whether it's 1.5 or 2.5%. I mean, I think that for us, the Lyman alpha forest has always been the higher risk, higher reward type of observation. It's it's a noisier, it's a systematically more difficult measurement than with the galaxies. On the other hand, it's a cheaper way to get to high redshift, so that's the plus of it. In terms of major systematics, I mean, I think it's all about continuum fitting and just making sure that we're not messing things up too much in the sense of introducing major tilts in the data. So I think that if we can get to a strong detection there, I don't think it actually has any particular systematics that are better or worse than the galaxy sample. But we are, with the Lyman alpha forest, effectively, if you were to convert it to a galaxy survey, we're effectively in the shot noise limited regime. Our grid of quasars is not sufficiently dense on the sky that we're getting a fully sampled IGM field. So that makes it a little different than what HETEX is going to be doing.
That's right, but you do have 100 or 150 independent points along each line of sight. So the sampling of space is
the
actually
sampling in the line
probably
of sight
denser.
direction is very good, and that actually leads to an interesting difference that with the Lyman alpha forest, we're actually more sensitive to the Hubble parameter than we are to the angular diameter distance, whereas normally for galaxies it's the reverse. And at high redshift, that's actually a good thing. The Hubble parameter is where the dark energy density is more immediately revealed. So this works out pretty well for that.
But do you get systematics from radiative transfer effects in the forest? This affects some of the other statistics.
I think you're absolutely right. It would affect other statistics. I don't think that it affects this thing very much because we tend to marginalize so aggressively against broadband tilts. I don't think that it actually. I fully would agree that it could be there for broadband type of signals, but our data would not be the best data for pulling out the broadband signals. I think that you really want the higher resolution, higher signal noise Lyman alpha forest data for that.
We have time for one more quick question.
So, Dan, in the second last slide, you pointed out 21 centimeter data, I think. So what do you expect to learn from those observations that you haven't already learned from optical surveys and BAO and BOSS?
So from the narrow point of view of BAO, once you've measured a particular volume, you've measured it. So BOSS will have measured a quarter of the sky out to redshift of 0.7 to very near to the sample variance limit for that. So, but the point of the 21 centimeter is to push out towards redshifts 1, 2, and 3. And I think all these groups are trying to figure out what is an efficient way, let's say financially efficient way, to measure the density field well at redshifts of 1 to 2, and indeed out to 3. And it just gets significantly more challenging to do redshifts 1 to 2 than to do the lower redshift galaxies. So the optical is working very hard, but the radio community thinks that it has a way to do this efficiently with the 21 centimeter line. And I think it's still, the jury's still out on whether that will work as well as they want, but it's a very interesting idea. When you go above redshift 2, the game changes a little bit observationally because the Lyman alpha forest is a Lyman alpha line in general is available, so it becomes easier to do this at higher redshift. But it's in the same. But honestly, the SKA is talking about doing 1 billion galaxies. To put a fiber on 1 billion objects on an optical spectrograph is pretty excruciating. So it could well be that the 21 centimeter is just the way to do this. That in 20 years we'll all be radio astronomers. It's not inconceivable.
Okay, I think we have to move on to the following speaker. So we thank again Daniel for the talk.